We now cover the subtopic linear, isotropic, and homogeneous dielectrics. So we start with the material that is said to be linear. The main item here is that D varies linearly with E, or the electric field strength. If you remember, we said this is electric flux density, and this is electric field strength. So we say that if this equation is obeyed, the material is said to be linear, and E or epsilon must always be constant. That is it for linearity. If material does not have epsilon as constant, then it is said to be nonlinear. Materials for which, now talking about homogeneity, materials for which permittivity or sigma, that is conductivity, does not vary in the region being considered. Like you have a material here, such that this would be your material. If you measured E at this point, at another point, at another point, at another point, and E is always the same, then the material is said to be homogeneous. This is different from the issue here, because the issue that we are discussing here is that if you vary E applied to this material and epsilon does not change, so you're applying E and epsilon does not change, and therefore you have D that is linear to these two. That is how when we define it as linear. But if we are not varying electric field strength, but we are varying the point of observation, where we want to find out what is our E at different points, and we find that at all points, at all occasions, E is the same, then we say that material is homogeneous. And the last point is in regard to isotropy. And isotropy means that if you measure E in this, if you apply E in this direction, and you find that you apply E in that direction, and you find that you get your D is equals to, as a given value, D1, you apply E in that direction, and then you apply it in another direction, say from downwards going up, and you find that this is your E1, and you find that D observed that is passing through the material is equals to D2. If D1, or in any other direction, if D1 is equals to D2 and E1 is equals to D2, except in terms of direction, then we say that the material is isotropic, and therefore it is independent of direction. That is the point. So we have at one point we are varying the direction, at the other point we are varying the space coordinates of observation. That is for homogeneity, and for linearity we are varying electric field strength. That is the major difference. Therefore, in material that does not, or that does not show that characteristic that D1 will be equal to D2, because it has different directional properties of epsilon naught of epsilon, then the material is said to be anisotropic. And anisotropic material is said to keep or observe this equation, that for different directions that are defined x, y, and z, we have parameters, or we have tensors that describes the permittivity along each direction. Therefore, D in x direction will be different from D in y direction, etc., etc. And in that case, we say that material D and E and polarization vector P are not parallel. And therefore, we say that this equation 537 describes an isotropic material. And one of the examples of an isotropic material is that crystalline materials and magnetized plasma are examples that demonstrate anisotropy. So we also define now formally a dielectric material in using the three terms: homogeneity, linearity, and isotropy. And therefore, we say that a dielectric material is linear if E does not change with applied field E. It is homogeneous if E epsilon does not change from point to point, and isotropic if epsilon again does not change with the direction. So we observe that the same concept of linearity, homogeneity, and isotropy applies to a conducting media that is defined by J is equals to sigma E. Of course, we know that J is the current density J, the vector. Sigma is the conductivity. This is not a vector. And E is the electric field strength. So if a conductor has sigma as its characteristic, or sigma is being the conductivity of that material, then we say that if sigma does not change, remains constant with E, then that material is said to be linear. Again, if you measure sigma at different points, and you find it to be the same, the sigma is said to, at all points, same at all points, then the material is said to be homogeneous, now being a conductor. And lastly, if sigma does not vary with direction, that sigma in the x direction is the same as sigma in y direction, and same as the sigma in the z direction, then this material is said to be isotropic. We also observe that most of the time we'll only be concerned with linear, isotropic, and homogeneous material. We will not be concerned ourselves with an isotropic material or in homogeneous media or non-linear media. So we are going to be dealing with such materials, and these materials are said to be simple materials. So for such materials, we say that the one that we have been derived so far, and particularly the one that we are dealing in chapter 4, the chapter 4 was concerned with the fields in a vacuum. Therefore, all the materials that we dealt with, we were describing the material with permittivity as epsilon naught. But now in this case, because we have a medium that has a constant epsilon, then we are going to be replacing epsilon naught with epsilon naught times epsilon r, and we have already defined epsilon r as the relative permittivity of the medium. And therefore, for instance, if you are to observe the Coulomb's law, the only item that will change would be introducing the epsilon r when you're dealing with a material that is simple, that is linear, isotropic, and homogeneous. And now we look at the example 5.6, and it reads that electric field intensity E is given by, or in a polystyrene having ER, or the relative permittivity is 2.55. The electric field intensity filling the space between the plates, a parallel plate capacitor, is this one. So our electric field strength is 10 kilovolts per meter, and the distance between the plates is D is 1.5 times 10 power minus 3. So the first question that we are asked, we are talking about a parallel plate capacitor. So the first question that we need to find out is D, and we know that we defined D to be given by epsilon E, and since we know D and we know E for now, our material medium we have said is given by epsilon naught, epsilon r. Therefore, we are given epsilon r, we know epsilon naught, so we just take the values and replace them where they should be, and that is how we do it here. This is the epsilon naught 10 power minus 9 all over that 36 pi, and this is our epsilon r, that's 2.55, and we are given that this is 10 power 4. This, of course, this is equivalent to 10 power 4 because kilovolts becomes 10 power 4. So we just do that multiplication and you end up with 225.4 nanocoulombs per meter square. So you always remember that the electric flux density is given in terms of coulombs per meter square. The second part requires us to find the polarization vector P. And if you remember in our last equation, we said that when a material that is polarized, it kind of promotes or increases the flux that is going through, or the electric field that builds up in the material. And therefore, we said that D in a polarized material is given by 1 plus psi E epsilon naught E. And this is what we characterized as our epsilon r. So if you just remember those equations, I will say that epsilon r is given by 1 plus psi E. And therefore, since we know this to be 2.55, then if you minus 1, you are going to end up with psi E. And this becomes 1.55. And for that reason, then we can simply say that polarization vector is normally given by psi E, epsilon naught, and E. And for that reason, that is what we have defined here. And therefore, we just replace the values directly. 1.55 times epsilon naught times the E, we get 137 nanocoulombs per square meter. And for that reason, we are able to determine the polarization vector. And now, in this case, if you remember that I have taken you back to our previous lecture 9, particularly because we observed that when polarization occurs in a medium, an equivalent volume charge density law V is formed throughout the dielectric, while an equivalent surface charge density rho PS is formed over the surface of the dielectric. And we referred the surface charge density rho S and the volume charge density rho V as bound surface charge and volume charge densities respectively. So in few words, we say that when a material gets polarized, it develops some what we have referred to as the bound surface charge density and volume charge density. And this appears to add to the, like I have material here, it has accumulated some polarization. So when you apply electric field here, if it has some free charges, then the flux that is passing through this material will be equivalent to the total the total charges accumulated or inside here, and they are in two forms. One is bound, that is arising due to polarization, and the other one is free, that is arising naturally, assuming that the material had some free charges. So for that reason, we're saying that the observed flux that is flowing through that material becomes more or higher. And for that reason, we are going back now to our question. So I've come back here where we have question that is referring to as the polarization vector and the flux. In that case, what we are about to find out is that there is some surface charge density due to free charges on the plates. And then there is surface charge density due to the polarization charge. So the surface charge density is arising due to polarization. The one we have called bound surface charge density. From the review I have just taken you back. And this is the one that appears normally if the distance between the plates has some free charges, then we have free charges. Therefore, we have surface charge density on the plates. Therefore, for that reason, this is going to be a direct result of flux, electric flux density, and the polarization charge is a direct relationship from the polarization that has developed on the medium or on the plate. Is it on the plate? Actually, it's on the medium between the plates, the polystyrene. And therefore, we have been able to see the relationship that the only difference is that the definition for the surface charge density due to the free charges is purely arising from the divergence, okay, the dot product of B, the electric flux density, and the unit normal to the surface, or the unit vector normal to the surface. And again, the surface charge density due to the polarization charges is arising due to the polarization vector that develops, and the dot product to the unit normal vector again pointing normal to the surface of the plates. For that reason, therefore, because we have already attained the D, we just drop the vector and we only give the value which is exactly what we found earlier. For the surface charge density of free charges, 225.4, and for the polarization charge, 137 nanocoulombs per meter square. And the last term is asking, or the last question is asking us to find the potential difference between the plates. And we know this to be given by ED, that is electric field strength times the distance between the plates. And therefore, we just multiply our 10 to power 4 multiplied by the distance, which we defined earlier as 1.5 times 10 to the power minus 3. And for that reason, we get our potential between the plates to be 15 volts. And that serves to illustrate the example of 5.6.